Section 7.7, Transforms of Periodic Functions. The goal of this section is to extend our previous Laplace transform work to periodic functions. So let's begin with a definition. A function f of t is periodic of period capital T if little f of t plus capital T is equal to little f of little t for all little t in the domain of f. So for example here, if you take the function f of t equals t squared, only the part of the standard parabola that has values on t from 0 to 1, we only look at that right half of the parabola. And then if we make a periodic version of this with period 1, we just think of copying and pasting this graph indefinitely to both the left and the right. Here I'm only showing the right. And this would be a periodic version of this function. Another example would be if you take something like g of t equals sine t on the interval from 0 to 2 pi, and you draw one cycle of the sine curve, then we think of this as having period capital T equals to 2 pi, and then we copy and paste what we see in that window, so to speak, that one period window. We copy and paste that to get the general periodic function. So here capital T will always represent the period, and we want to see about Laplace transforming these kinds of functions. So suppose little f of t is periodic with period capital T, then first we need to define the windowed version of little f of t on the interval from 0 to capital T, and the windowed version just says, and we will denote it by f sub capital T. So this is how you can tell the difference between the full-blown periodic f and the windowed version. That the windowed version agrees with the original function on 0 to capital T, so on an interval with whose length is the period, but outside of that window, outside of that one cycle, that one period, the function is 0. So let's visit this concept of the windowed version of a function using the examples that we just did above. So here when we talk about taking little f of t equals t squared on the interval from 0 to 1, we're looking at the right half of the standard parabola, but we're only taking that graph on the interval from 0 to 1. So then if we were going to create the periodic version, we would just copy and paste that indefinitely to the right and to the left, generating the periodic function like the one we saw up here. But the difference between the full-blown periodic function and the windowed version is here we just want to take one period. We want to grab the one period of that function and we want to zero it out outside of this highlighted window. So here, the windowed version of that function would have the formula little f sub capital T is t squared on 0 to 1 and 0 otherwise. And graphically, we would get one cycle on 0 to 1, and then outside of that highlighted window, the function needs to be 0. This is the key difference between a full-blown periodic function and the windowed version of a periodic function. Is the windowed version is only capturing one period. That's what we're thinking of. We're viewing through this window, one period. And very, very important is that it zeroes the function out outside of the window. So similarly up here, when we were looking at the full-blown periodic version of g of t equals sine t, if we want the windowed version of that, g sub capital T, then what we would do is just visualize one period. We want to grab this function inside this window of length 2 pi, and we want to represent that function inside the interval, but then we want outside of that, we want it to be 0. So when we do the windowed version, we get the one cycle of the sine curve on the interval from 0 to 2 pi, but outside of that, we want the function to be identically 0. So we would take the function that is 0, that is sine t on 0 to 2 pi, and then outside of that interval, it would be the function that's 0. So one of our goals here is we eventually want to Laplace transform these, because eventually these could be the forcing functions that appear in the right-hand side of our differential equations. So in order to do that, we want to represent these kinds of both the windowed version and the regular function, most importantly the windowed version. We want to represent the windowed version in terms of unit steps. So why don't we, as an exercise, let's take the same two examples that we just worked with, this little f and this little f sub t and this little g sub t, the windowed version of these functions, and let's write them in terms of unit steps. Well, just looking at this picture, and if you think back to the philosophy we had when we started doing this, that what we want is we want the function to be 0 to the left of t equals 0. So we need a switching event to occur at time 0. So what we're going to do is write little f sub big T as a unit step. So this is a switch that turns on at time 0. When it turns on, we want it to turn on the function t squared. So we have the function t squared here. And then we want it to stay on until the next switching event. The next switching event occurs at t equals 1. So we're going to add a u of t minus 1. That's a switch that turns on at time 1. And what we want to turn on at that time is we're just trying to zero the function out, so we need to undo whatever was already on. So what was on was a t squared, so we're going to subtract off a t squared to get a net value of 0. So you could leave it like this, or you could rewrite it maybe like this, or even factor the t squared and write it like this. These are just cosmetics. Any of these is fine, but this is how we would write the windowed version of a periodic function in terms of unit steps. So why don't we try it again with this g function? So with the g function, let's say it before we write it down. We want a switch to turn on at time 0 because to the left we have to make sure that the function is 0 to the left of t equals 0. So we'll start with a u sub t, or a u of t, and then what we want it to turn on is the sine function, so we'll multiply by sine t. We want to leave that on until the next switching event would occur at time t equals 2 pi, so we want to add a u of t minus 2 pi, add a u of t minus 2 pi, and then what we want that function to do, or what we want this switch to accomplish, is we want to turn off what was already on. Since a sine t was on, we're going to multiply this switch by a negative sine t so that it'll offset the sine t that's happening here. Notice that that's going to zero the function out and keep it 0 forevermore, so that's what we want. So this would be the representation for the windowed version of little g sub t, and you could leave it like this, or you could rewrite it like this, or maybe even factor out the sign. Again, these are just cosmetics. Okay, so our next goal is to calculate Laplace transforms of not just windowed versions, but we want to calculate Laplace transforms of full-blown periodic functions when we know the period. So in preparation for doing that, we have a new theorem. This is a new entry in our table, and it simply says, suppose little f of t is a periodic function with period capital T, so this is the full-blown periodic function. Then the Laplace transform of the full-blown periodic function is the Laplace transform of the windowed version divided by 1 minus e to the minus s times capital T. So that's what that notation means. Here, big F sub capital T means the Laplace transform of the windowed version of little f. So this is something that would be provided to you, so we just need to focus on how to use this. And you can see that the key parts are, and the proof of this is in the text, I won't go through it here. The key parts are, you need to, when you have a little f of t, you need to rewrite it in terms of unit steps. You need to rewrite the windowed version in terms of unit steps. So you have a little f of t, you need to get the windowed version, you need to write the windowed version in terms of unit steps, and then Laplace transform the windowed version, which would be this, and then divide that result by the quantity 1 minus e to the minus s times your period. Let's look at some examples. So let's compute the Laplace transform of this periodic function f, and notice the periodic function could be given to you in terms of a formula, it could be given to you in terms of a graph. You'll see both kinds in the homework. So here what we're trying to say is we've got a function that's 0 to the left of t equals 0, and then what happens is it's going to go 1 minus 1, 1 minus 1, 1 minus 1, and it's doing these each on an interval of length 1. So the dot 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 here is very, very important because it's telling you that this pattern is repeating and it's actually a periodic function. So the first thing we need to do is spot what one period is. A common mistake is to think that this is one period, but this isn't one period because if I copy and paste this to the right, I don't get the curve. So what I want is I really need both of these. If this is my window, and I want the smallest window, this is the smallest window that'll work, so my capital T is 2, and notice if I copy and paste what is sitting in this window, I'll get it again here, and again here, and again here. So this is the windowed version graphically. It's very important that we have an accurate vision of what the windowed version is before we write down its formula in terms of unit steps. So now writing this down in unit steps, We'll just talk through this. Well, we know we need a switching event to turn on at time 0. When it turns on, we want to turn on a 1, so we'll do u of t times an understood 1, plus the next switching event will occur at time t equals 1, so we need to switch u of t minus 1. And when we do this, now we want to go back to our old philosophy, and you could do this in terms of the rectangle function that we talked about before, but here I'm just doing this according to my preferred philosophy as I discussed in the previous section. So what I want to do here is when I turn on this switch, I want to go back to 0, so I want to undo what was already on. That gets me back to 0. And then I want to add on where I want to be. I want to be at a minus 1, so this zeroes it out. This brings me back to a minus 1, and this is getting me this part of the windowed version. Now here's a little difference that we didn't see in the previous two examples, and we have to be very, very careful about, is it's your responsibility to make sure that the windowed version actually zeroes out when you get outside of the window. Notice if we just left this right here, then the windowed version, this would just keep going forever because nothing turned this minus 1 off. And this is not what the windowed version does. The windowed version has to zero out outside of the window. So we need to add on a new switch. It occurs at time 2, so we're adding on a u of t minus 2. And what do we want to do? Well, we're trying to undo this minus 1 that is turned on, so we'll just add a 1. And that will give us a net result of 0 when we're to the right of 2. We could rewrite this as this, and this would be our windowed version of little f written in terms of unit steps. Now we're not done. Remember, according to our theorem, what we need to do is once we need to calculate the Laplace transform of the windowed version, and then we need to divide by 1 minus e to the minus s times my period. So we'll go back, and we've calculated the windowed version, and now we will calculate the Laplace transform of the windowed version, thankfully, and you can see why we wanted to write this in terms of unit steps. This is very straightforward. We just use our basic table entries. Remember the Laplace so the Laplace transform of this is the Laplace transform of this. We'll call this big F sub t of s. We're just going to Laplace transform the pieces using linearity and factor out the constants. We know that the Laplace transform of u of t minus a is e to the minus as over s. Here my a is 0, here my a is 1, here my a is 2. So these are very easy Laplace transforms to compute. So if you want to, we can clean this up, rewrite it like this, and this is my big F sub t. Now we're not done. To get the Laplace transform of the overall periodic function, we need to take the Laplace transform of the windowed version and divide through by 1 minus e to the minus s times my period. Here my period was length 2, so this is just going to take, I'll copy and paste this right here, and then I'll have 1 minus e to the minus 2s. Don't forget this part. It's a very common mistake that people make here. Okay? So we can see that the real heavy lifting here is identifying the windowed version, accurately writing the windowed version in terms of unit steps, Laplace transforming the result. That gives us the numerator of our final answer, and then just don't forget this denominator part as well. Let's look at one more. So if we have the function f of t equals t squared on 0 to 1, so this is our half parabola example. We'll take our capital T to be 1. Then we've already rewritten this in terms of unit steps. Here you go. If we take the Laplace transform of the windowed version, it's just the Laplace transform of this. This we'll call big F sub t. Here we're going to use linearity to take the Laplace transform of the pieces. So the Laplace transform of this piece minus the Laplace transform of this piece. Notice if you go back to our previous work, this is, remember we had when you were Laplace transforming a function times a unit step, you either had the F version of your theorem or the G version of your theorem, the F of t minus a times u of t minus a, that's when the shifts match. Or you had the G of t times u of t minus a when the shifts did not match. So here we can see this is an example where the shifts do match, and the shift here is 0 in both. So our theorem says that you just want to do e to the minus as times your big F of s minus your a. So here we have we identify what our little f of t is. Our little f of t here is t squared. Our big F of s, we just Laplace transform this. We get 2 over s cubed. And when we go to do this, since there's no shift, there's not really much to do here. We get this. And then when we When the shifts don't match, then we can see here that the shift here is 1, the shift here is 0, the shifts don't match. Remember, we need to identify what our g of t is. We need to look at our g of t plus a, so here g of t plus 1. If this is g of t, then g of t plus 1 is this. And now you might pause for a second. How in the world do we take the Laplace transform of this? You do need to remember that algebra is your friend. This is not in our table, but if we just expand this using algebra, we get this. And now we can take the Laplace transform of our g of t plus a. That's just the Laplace transform of this. By linearity, we take the Laplace transform of the pieces. These are all things that are in our basic table, so we're quickly able to get the Laplace transform of this. So then we get, from our g version of our theorem, we get e to the minus as times the Laplace transform of g of t plus a. So here you go. So we put the Laplace transform of this piece is this, the Laplace transform of this piece is this, and we'll just write it all together, clean this up a little bit, and here's what we get. Now this is just the Laplace transform of the windowed version. We're not done. To find the Laplace transform of the overall periodic, you take the Laplace transform of the windowed version, which is right here, and you divide by the whole thing by 1 minus e to the minus s times your period. In this case, our period was 1, so we get 1 minus e to the minus s. This would be a perfectly acceptable way to leave your answer. One last example to see how to handle, this is our sine example from the very beginning of the notes here. If you take g of t to be sine t on 0 to 2 pi, so this is one cycle of the sine curve, our capital T is 2 pi. Well, we already wrote this in terms of unit steps. Here you go. If we take the Laplace transform of this windowed version, it's the Laplace transform of these. By linearity, we can take the Laplace transform of the pieces. Once again, you're going to see this common theme. Here our shifts do match because there's no shift in either one. So our a here is 0. So this is my little f of t. I find the Laplace transform of that from my basic table. It's 1 over s squared plus 1. And I'm almost done here. I know that this Laplace transform to e to the minus 0s times 1 over s squared plus 1, just using our f version of our theorem. And then over here, we see that the shifts don't match. Here there's no shift. Here there's a shift of 2 pi. So my a is 2 pi. I'm going to use the g version of my theorem. I need to identify my g as sine t. If g of t is sine t, then g of t plus a is g of t plus 2 pi. That's sine of t plus 2 pi. And I wanted to include this example. This is going to occur in the homework. When you get right here, you might get stuck because you think this is not table friendly. This is not in my Laplace transform table. Well, just like in the last example, we used algebra to help us out. You do need to recognize that this is just sine of t plus 2 pi. And since sine is a 2 pi periodic function, this is just a fancy way to write sine t. And if you don't see that, then you can get stuck here because you don't know how to finish this. But you do need to recognize that this is a periodic function, and since it is, this is sine t. And now I will find the Laplace transform of my g of t plus a, which is the Laplace transform of my sine t. It's 1 over s squared plus 1. Now we use the g version of our theorem. This minus is here. We use the g version of our theorem, which just says e to the minus as, my a was 2 pi, times the Laplace transform of my shifted g. This is the Laplace transform of the shifted g. So now it's just a matter of finishing things out. We can clean this up just a little bit. And now the overall Laplace transform of the periodic function is the Laplace transform of our windowed version divided by 1 minus e to the minus s times the period. So I'll just copy and paste this in for my numerator. And my denominator is this with my capital T was 2 pi. Now if you stop here for a second, one of the reasons I included this example is you look at this and this looks very, very fancy. And you might say, well, hold on a second. If we're doing the periodic version of one cycle of the sine curve, the periodic version of one cycle of the sine curve, if we just go back up here, so here's the windowed version, and if we repeat this pattern, one cycle of the sine curve, we're going to get the actual sine curve. And we already know the Laplace transform of the actual sine curve of sine t. It's 1 over s squared plus 1. And so you might say, well, how in the world is it true that this gives me the Laplace? This is really just an overly fancy way to say the function sine t. We're doing the periodic version of the of sine t on 0 to 2 pi. That's an overly verbose way to say the regular sine function, and yet when we use this methodology, we got this very complicated looking Laplace transform using this periodic theory, and yet we know that the answer ought to be 1 over s squared plus 1. So, what's the explanation for that? Well, here, they're both correct. If you were to do a little algebra on this and simplify this, the exponential terms here all cancel out, and you would see that this simplifies to this. It just takes a little bit of work, but both of them are saying the same thing. This is just a different way to say this. You do need to check that and see. And so you're seeing that we can tackle some old problems in new ways, but that wasn't really the point. The real point of doing this was to tackle problems like the periodic half parabola or this so-called square wave that's very common in electrical engineering and other forms of engineering, these kinds of things. These would not be things that would be doable using our previous Laplace transform techniques, but using this windowed version and our new theorem, we are able to tackle these, and once we're able to tackle these, that means that they can be included as forcing functions in our differential equations and initial value problems, and we'll know how to take the Laplace transform of that periodic function on the right-hand side.